We have the Darcy-Weisbach equation in our document. Now we can actually start the dimensional analysis. The first step to that is defining the dimensions for each of the variables in the equation. And it would be good to have that notated directly in our report right next to the variable. So we can start back up here at the top where we have an equation for bar u. And I'm just going to go ahead and put this on its own line just because it's going to get kind of complicated. And I want to make sure that it's easy to read. And I can just add to the mathematical notation here the dimensions that I want to put for an average velocity. Now the dimensions for a velocity are going to be a length traveled per unit time. So ultimately it's going to need to look something like this: an open square bracket, because dimensions should be in square brackets, an L for length, a T for time, and an exponent for the time being in the denominator. So a length per time means we need a -1 exponent on the time. Now the way you do an exponent in LaTeX is with an upward caret. And again, if you have multiple characters you need in the exponent, you might need some curly brackets to say all of the characters that should be in the exponent. And in this case, I need a -1. And finally, I need to close that with another square bracket on the other side. So I've got length per time designated as dimensions, but this is not quite going to be good enough. And let's take a look at a preview to see why. If I run the preview, we're going to look at that U and we can see how everything is run together. Like everywhere where I had a space in my code, remember spaces get ignored, there's no space. So we really want a little bit of space between the average velocity and the open bracket, and we really want a little bit of space between the L and the T. So to make this clear, and finally, we really want to make sure that the L and the T are not italicized. Remember, dimensions should not be italicized to make sure they're distinct from variables. So let's figure out how to do all of that. Well, first of all, we really don't want any letters within these square brackets to be italicized. So we can take care of that using another escape character code. In this case, it's going to be mathrm. That's removing mathematical notation from what's inside the curly brackets following mathrm. So I'm going to put mathrm before this and put curly brackets around the whole thing so that no letters are looked at as variables in between those curly brackets. Also, remember we talk about space being ignored, but we want some space between the dimensions and the variable. And the way you can purposefully add space is with another special character. It's the tilde character, the little squiggle character. So if we put a tilde, that will add blank space to the equation between the terms divided by that tilde character. So that should give us some space between the bar U and between the open square bracket. And we also want some space between the length and the time. So again, I'm going to put a curly bracket in between those. Now remember, all this extra space that I'm adding here doesn't actually mean anything, but it does make the equation a little bit easier to read. So now I have length per time. I'm going to go ahead and put a little space there too, just so that I can see things a little better. And that should take care of it. So let's see how we did in terms of getting rid of the italics and adding space where we wanted space. I'm going to go ahead and do a preview. Okay, that's looking better. We've got a space between the U bar and the dimensions, and we have a space between the L and the T, and our L and our T are no longer italicized because they're not using mathematical notation anymore. And we have an exponent with a -1. So that's looking pretty good. I'm going to close that. I'm going to clean this up a little bit. I'm going to leave that on its own line, but I'm going to go ahead and close this down so it doesn't have too many extra lines. And I just think it's a little easier to read this if I leave the math on its own line, even though it's in line with the rest of the text when we render it. Okay, so that takes care of the average velocity. Oh, one more thing to cover here. Now this all looks fine, but the reason that it looks fine, I'm going to do a preview again here, is because everything that's within the square brackets is just one line of an equation, and therefore regular square brackets work just fine. However, when you start doing exponents, and especially when you start doing fractions, the amount of vertical space an equation takes up can change. So if there were a fraction in here, this would be taller, but the brackets would still be the same size, even though what's inside the brackets got bigger. So if you want brackets that will scale with the size of your text, and in this case, it's going to be a subtle effect because what's inside the brackets is just one line of text. But there's a way to specify brackets that scale, and that's to put, again, an escape character and a left in front of the left bracket, and an escape character and a right in front of the right bracket. And that code means a scaling left bracket, and this code means a scaling right bracket, which means they'll get bigger and smaller depending on how big what's inside the brackets is. So I'm going to do a preview on this, and it's probably not going to look significantly different, but if you look carefully and you do this yourself, you'll see that it's a little bit bigger. And it's a little bit bigger because the exponent makes the text a little bit bigger, and it needs to make the brackets a little bit bigger so that looks right. So that's just something it's a good habit to get into for parentheses and brackets, anything like that, is to use that left and right notation just to make sure if the stuff that's inside the brackets or inside the parentheses gets bigger, your parentheses or brackets will also get bigger. Okay, we need to put dimensions for all of our variables now. So we've got gravity, and I'm going to go ahead and put my tilde there to make sure I have a little bit of space between the g and the dimensions. And I'm just going to go ahead and borrow this whole notation for length per time, because remember, acceleration is length per time, or length per time squared. So it's just a minor change from the dimensions of velocity. So if I take my notation for the dimensions of velocity, remembering to grab the math RM part, and I pop it in here with g, I'm going to use multiple lines for this list item and indent it so it's easier to read to see where the list item starts and stops. And I just need to change this t to the -1 to a t to the -2, because a acceleration is a velocity per unit time, which means it's a length per time squared. And I've already got length per time. I just need a -2 on the t to make it length per time squared. So let's double check that that worked. I'm going to preview it. And sure enough, gravity dimensions length per time squared. And again, you can see that the square brackets are scaling a little bit to accommodate that exponent. Okay, the next one is our hydraulic radius. And I'm going to go, again, use the notation from before, even though this one needs to be a little bit different. And we specified this as a area per unit length, or the cross-sectional area of the channel per length of wetted perimeter. So that means I need an exponent in my numerator, and that's going to be a length squared, because that length squared is an area. Now technically I don't need the curly brackets here, but sometimes I just put them in just to make sure that if ever I add another character in here, it will all be in the exponent. But you could just put a 2 without the curly brackets, and that will still work. And instead of a time in the denominator, I need a length in the denominator. Again, it's an area per length. So I can also do what I did before to keep my code neat. I'm going to add a new line here to make sure I can see all of my code without having to scroll over. And let's see how we look. We've got a length squared per length. And we can go ahead and show that as being simplified, because we know that a length squared per length, one of the lengths in the denominator cancels out with the length in one of the lengths in the numerator, and that just leaves us with a length. So, and we can show that right here. So maybe we'll put an equal sign here, and we'll put a left bracket and a right bracket. Sometimes I put both brackets every time before I fill them in just to make sure everything is complete in terms of what I need on both sides before I fill in the middle. And I just need an L in the middle for length. So let's see how that looks. Excellent. So I've done a little bit of a derivation right here where I recognize that the hydraulic radius is defined by an area over a length, which simplifies to just being a length. Similar to that, I'm going to again borrow notation from before by cutting and pasting or copying and pasting. And a slope is going to be a length of rise over a length of run. So I've got a length in the numerator in this notation already. That's correct, but I need a length in the denominator. So that's a length per length. And also, just like before, I could go ahead and do that derivation right away and show that in square brackets left and right. If this is a dimensionless ratio, a length per length, I can just put a 1 in those square brackets. And again, I want to keep my markup code neat. I'm going to add an extra new line there and tab over. And I'm going to be brave and go ahead and do this for my F. F is just a dimensionless ratio. So I'm going to go ahead and copy in my notation, but all of this length per time stuff in this case is just going to be a 1 because the friction factor is by definition a dimensionless ratio characterizing the effect of friction. And to be consistent, I'm going to add a new line here just to keep my code narrow. So let's see how that's all working. Okay, average velocity, length per time, acceleration due to gravity, length per time squared, hydraulic radius, an area per length or just a length, the energy slope, a length of rise over length of run or a dimensionless ratio, and finally the friction factor is defined as a dimensionless ratio. So we've got the dimensions for all of our variables plugged into our document and showing up with nice professional mathematical notation.